So today we are starting this webinar. I'm very happy, as I said, because we have, I think it's a cutting edge company that is going to present us something, I repeat, for me, very innovative, very new. I do not know so much, so I'm very happy to be here today to learn together with you. We are talking about artificial intelligence, vision, perception, segmentation, a lot of things that could sound very, very new, innovative, but I think that is we landed into the mobile robot business. It makes a lot of sense and is very, very important. I have here, you can see two people there. We have Asaf and Jack from RGo Robotics. They are going to present us their technology, and they are going to show us what are the capabilities and how do they improve many things in our typical AGVs AMRs. I just leave the show to Jack and Asaf. Please introduce yourself. Let us know who you are. What about RGo Robotics, please?
Hi. Good morning, good afternoon, good evening, or wherever you are. Nice to meet you. I'm Asaf Agmon. I'm one of the co-founders of RGo Robotics, and I lead the engineering group here and product management that includes product development, custom enablement, and also product management. With me here is Jack. Jack, go ahead.
Hey everyone, my name is Jack Miller. I'm an application engineer with RGo. I've been in the mobile robot space for the past 6 years and automation in general for the past 12. So a little bit of background there, and I'm involved in customer enablement and getting integrations going for all of our partners. Thanks.
Okay, good. Should we kickstart the presentation? Thank you.
Okay, good.
Okay. So now that we covered the introduction part, I want to talk a bit about what we're going to talk about today, and then we're going to talk about what I told you I'm going to talk about, and then we're going to summarize what we talked about, right? So what are we going to talk about? We're going to show you a bit how we see the challenges in mobile robotics today from computer vision perception and AI. We're going to tell you what RGo does, and we're going to tell you what are the challenges that we're looking to solve and improve in mobile robotics and perception, focusing on coverage of system where they can operate, focusing on deployment and commissioning, and making sure these are simple and streamlined processes, and how it's so easy to integrate and operate. Overall, the main focus here is going to be how we are trying to solve the scalability issue and how we're trying to significantly improve scalability of robotic autonomous systems using intelligent perception. Then in the end, we're going to talk a bit about how we're using AI with the upcoming generations of our products to further take this into the next generation of products. So RGo's mission statement, what do we do? What do we want to solve? We want to make robotics adopted. We want to make them enable mass adoption of intelligent automation using AI based on human level perception that we create with computer vision, AI, and sensor fusion to enable robots to truly understand and truly interact with the world around them, right? The basic notion assumes that in order for autonomy to be really scalable, to really work across all sites and all required operations, you need intelligent perception, as information is the key to understanding and to operation. This is a good summary. So we're going to talk a lot about many things, but if this is becoming too much, just remember two things, and we can talk in details in private if you want to set up sessions. We enable robots to operate anywhere, anytime. We enable and unlock difficult environments where previous technologies suffer and limit. And our mission is also to accelerate commissioning of mobile robots. So if these two are interesting to you, let's talk. Now, as far as the challenge, so the challenge that RGo is focused on, as I said, is to enable scalable autonomy. And I'm going to be saying scalable and scalability a lot here. And the key concept here is that things need to operate, and they need to operate seamlessly. Robotics is a lot of AMRs and AGV are focused on industrial manufacturing, but also on logistics and other environments. and they have strict requirements on operational availability, but also on coverage. And to enable that, those systems need to be always up, they need to be always available, they need to be super robust, but they need to also operate anywhere. If you look at a lot of the automation today, it's done on a very, very limited set of environments, in very limited set of functions in these environments. And we believe that to scale this up, this needs to be much wider. Think about the food industry today is almost uncatered for as far as automation. Automation is really focused on environments that are structured, that have facilities that enable robots to simplify the problem statement and to be able to operate in a reliable manner. We want to solve that and we want to extend that. We want to make autonomy that works always and anywhere. But at the same time, there's another challenge that is often considered as a second step, but we believe it's also a basic part of autonomy, is that it needs to be scalable as far as deployment. It is very important to get an autonomous system to operate in an environment, but it is just as important to make it usable and deployable by the scale of people around us. We all know that skilled force is a hard resource these days, especially in the last 5 years, but even more so, even before that, it is crucial that those systems can be deployed by anyone and not just by super skilled employees that then require, that limits the deployment cycles. So we went on and analyzed how the market looks like today. And this is even just focused on material handling. And with that focus, we analyzed that about 5% of the market, and I think we can all agree it's a single digit. Some may claim it's 1%, some may claim it's closer to 10%. We can all agree that the market coverage today of autonomy is very limited. The market reach, the actual activation rate is very minimal. Even more so if you consider not just sites that were activated, rather operational flows that have been automated, fully automated, it's very limited. Think about food, as I said, the food industry, think about outdoors, think about the hotels and service robots, think about all those applications today that are still human operated that could be automated with autonomous systems. Okay, a lot of that is because current automation requires a structured environment. They require the environments to be relatively static and not change, and they require them to have some often infrastructure installation that also creates more challenges, and they need the environments to be predictable and without a lot of movement. If you go to those dynamic environments where there's a lot of human traffic, a lot of traffic overall, a lot of dynamic elements as far as moving objects or obstacles, if you go to unstructured environments, if you go to environments that change over the weekend, so you might have a manufacturing site that needs to change on a weekly basis based on what they manufacture. Those systems today need to be reprogrammed or recommissioned, and they're not adaptable. And that significantly limits the coverage of the current automation systems. And then you also add to that indoor, outdoor, and different surfaces, and you realize that the coverage of current systems is very limited. So the first problems we'll try to solve is the coverage. So making autonomous systems operate anywhere, anytime, would unlock the first step into making sure this market is also addressable. Okay. And with that, the second problem will be adaptability. Okay. Those two together cover these two together basically build the coverage. Okay, so improving the availability of systems and improving their adaptability means they can now cover all the different sites. The next challenges that we have are the commissioning times and the long time to market. So once you've solved the availability and coverage, as I said, you still need to talk about the scalability of the solution that you have, how easy it is to use it and how easy it is to deploy it. Okay. And what RGo does, and we're going to go into the details today, and that's going to be the outline of the story that we go through, is how do we move from what we designate as autonomy 1.0 to autonomy 2.0? Autonomy that is available everywhere all the time, autonomy that can automatically adapt to changes without user intervention, without recommissioning, autonomy that is just simple to deploy. You have tools, they're simple, they're easy, they're intuitive, they don't require skills or expertise. And furthermore, you get fast time to market with lower TCO. It is RGo's mission statement to solve these problems and make this a reality, because solving all of these together would mean that autonomy would be able to scale and increase the market size eventually. Jack, over to you.
Thanks, Asaf. All right, so reliable autonomy. So we believe reliable autonomy is the foundation of solving availability and adaptability issues in the field today. So how do we address it at RGo? All right. So we offer a full stack perception engine that leverages visual data fused with IMU and odometry sensors to answer the questions, where am I, where can I move, and what are my surroundings? So what does that mean exactly? It means that we are able to map and localize any wheeled vehicle in any environment, as well as recognize and classify different objects seen in operation. We do this while operating on affordable and scalable hardware that resides entirely on the vehicle. So everything's on the edge. In the bottom right corner of the slide, you can see two of RGo's hardware offerings. The monocular system on the left, which requires wheel encoder odometry, and the stereo system on the right, which derives its own visual odometry. So now we'll get into some of our partner companies and some of the major challenges that they face and what ultimately led them to RGo. So WheelMe is a great partner to highlight for very dynamic and unstructured environments. Go back to video one there. Let's see here. See if you guys can see this for me. All right, so this is a video of WheelMe in operation. I'll stop it right here, and you can see there's tons of pallets. There's pallets staged on the floor. There's wide open spaces that have various product moving around, right? There's a lot of activity. So in this particular area, we're going to have staging carts, right? So ultimately, from a WheelMe perspective, right, their platform has a lot of different sizes, a lot of different shapes based on the specific use case. Means that they need a very adaptable and easily configurable solution. You know, WheelMe initially tried several open source options before selecting RGo. None of the open source options, LiDAR or VSLAM, were robust enough to manage the changing environments that they were involved in. And that's a big part of their actual market space. Go back to presentation. All right. So the next partner that we'll talk on is RGo Robotics. So Capra is another great example of very dynamic use cases. As a platform, their focus is intralogistics between buildings, where they are exposed to various lighting conditions, open unstructured spaces, changing temperatures and humidities, very dynamic adverse conditions. As such, they really needed a reliable and adaptable localization solution. So we'll go ahead and play the video here for Capra, and we'll go through some of their actual activities. So you can see in this particular case, wide open area, changing environments, pallet stacked. There's cobblestone streets, and then it goes to flat areas. So vibration changes, lots of different infrastructure changes, especially what would normally be at a 2D LiDAR level. And we're able to maintain very precise and very accurate and repeatable positioning throughout all these dynamic changes. Now we're getting into some more obscure and really torturous kind of environments, food processing. So think of this as, there's going to be temperature changes, right? The meat's got to stay cold. It's wet. There's meat hanging all over. It's moving on different hanging hooks. So very dynamic, very changing. But again, another environment that we're able to help Capra to succeed. All right. We'll go back to the presentation. All right. Okay, so next partner we'll discuss is Onward Robotics. So Onward is a good example of another major pain point for competing technologies, right? And that's repetitive narrow aisles, right? So we discussed the dynamic situations with the previous two. Now narrow repetitive aisles is really the second biggest pain point from a LiDAR perspective. Right, so Onward is a pick-to-light mobile robot that operates largely in e-commerce and distribution centers. So as such, their environments are typically large warehouses, and all the racking looks the same. Right, so not a whole lot of differentiation, especially from a LiDAR perspective. You would see pretty much the same iterative racking columns and boxes, but from a vision perspective, we're able to really hone in on the nuances between all the different edges and everything. So really provides a much more robust solution. And just to kind of add on to that, Onward actually started with an open source LiDAR-based SLAM known as Cartographer. But they often ran into pose jump issues and lost pose issues, particularly while they're going down long, narrow aisles that look identical, in a grid format. So that's why they actually selected RGo, was really to adapt to that pose jumping issue, right, and really understand where the robot is, no matter what aisle it's in. All right. So then the next, we'll call it the next industry that we'll discuss on here is the sortation robotics and as well as the infrastructure AGVs. So these are two very different industries, but we've seen a lot of interest in the sortation robotic space, particularly recently. We currently are partnered with a couple of OEMs in this space, and we actually have a few evaluations coming up for a few others. But ultimately, what we've seen in this space is these robotics have for a long time navigated based off of little QR codes on the floor, right, which is its own type of infrastructure. And that's a pain to maintain, right, especially in operations, especially when you have hundreds of these robots moving around, right? Stickers peel up eventually. So we're seeing a particular need in this industry and a particular response in this industry to adapt to an infrastructure-less solution, and that's where we come in. So again, these types of environments are going to be very repetitive, right? Very narrow at times. We need to maintain tight precision and tight position accuracy, and dock to the right locations. So we're pretty excited about this industry right now. We think that we're bringing the right technology to the table. So that'll move on to the AGV. What's typically a mag guided, line guided based system. Right now, we believe that there's an opportunity to we'll say, evolutionize this industry and these players to move from what is typically a physical line guided system to what is more of a virtual line guided system, right? So it all comes down to how long the deployments are taking, right? The installation project schedules are kind of a nightmare at times, right? And so the infrastructure that's required just requires a lot of skilled labor. requires a lot of planning ahead of time and requires a lot of precise execution during the deployment phase. So that's where we believe we can bring a more, say, helpful and robust solution that does not require the infrastructure that often causes the project schedules and delays. And so the next element that we'll touch on is outdoor. So we are capable of indoor and outdoor, as we mentioned with RGo Robotics. I'll play a video here for you, but to set it up, this is actually our system attached to a car driving through a parking lot and into a parking garage, and going down a ramp into it's an underground parking garage.
want to maybe recapture and go through what we saw. So I think overall, over all the videos, what we saw is that the RGo perception engine provides localization that enables robots to operate anywhere, anytime. That means they can run indoor, and you saw outdoor. You saw a very interesting example of our perception engine mounted on a vehicle driving through a parking lot, then into an underground area, and then back out. And it operates in different conditions and environments and weather. And it just provided high precision with or without RTK fusion as well. And that means that a robot manufacturer can, instead of worrying about localization, worrying about the robot being able to operate anywhere, anytime, can rather rely on the RGo perception engine, integrate it, and just get accurate position that operates, enables it to just operate, right? And enables you to focus on value creation from the robot perspective and not just about getting it up and running. And with that said, we're solving the basic problem of just being able to operate. We also want to make sure that we enable the next level of scaling by simplifying the commissioning process. And I don't want to jump into assumptions. I think we have a survey here. And Alfredo, if you can set it up, I'd love if the audience could take a moment and give us what your thoughts. Why would you like to see the improvement in the commissioning process today?
Yeah, I mean, we have we would like to know what is your feelings, okay, when it comes to install, to deploy mobile robots, typical engine installation. So what would you like to improve in your commissioning process? Okay, so maybe you would like to make it shorter, avoid having an on-site engineer, be more accurate, more precise, to avoid maybe some tweaks after all, or everything of above, because there are all these kind of problems are leading you to in cost increase and having more issues in the afterwards once the system is going, for example, or maybe for you everything is working right now perfectly and you don't have anything to improve. Okay, so what are your main concerns, your main problems that you are facing while commissioning, and what would you like to improve? Okay, so just to make us know what is your feeling, just 1 minute, just please vote, participate, because your opinion is always important, because I used to do a lot of polls in GV network, in internet, etc., and always what I think is never what or almost never what the audience is thinking. So it's very interesting to know different point of view and what is your, because it depends on your own experience. Okay, so well, I hope you well, there is quite a lot of votes right now, so let's see. Okay, if you are okay, Asaf, we can close the vote now, and just to see what is the main, what is people saying. Okay, and voting. Okay, give you 1 second. Come on. Okay. And
yeah,
voting.
So far it's pretty even distribution, I gotta say. So
yeah. Okay, I see already the results. Asaf, 1 second. Let me check. Can you see results? Okay. Yeah. Okay.
I think you guys voted that basically you want to make it shorter, you want to remove the need for the engineer, you want to make it more accurate, you want all of them.
Yeah, I mean, it's something. I mean, it's good to know that. I mean, there is not only one single issue.
Exactly.
It's a mix of all of them. Okay, I can agree. Okay, what is you have some feedback? What did you thought, Asaf?
So I think it really goes in line with the way I see it, and I think there is one word that simply captures it, and it's the word simple, right? It needs to be simple enough so that it is short. There's no engineering needed. It's accurate. In other words, you don't need to worry about it. Okay, and it is very apparent that whoever voted, at least 53% of the folks on this call, think it's not as good as it needs to be. Okay, and I think that's coming out clear.
Oh, that's clear. For sure, there's always room for improvement, and that is why we are here you today. Okay, so I just close this. Give me a second, and I come back to the presentation. Give me one moment. Presentation. Here it is. Okay, so we left. We continue where we left.
Yeah. So diving into site commissioning, and again, this is our experience working with our customers and our partners on scaling our deployed solution, right? And as we scaled our deployments, we realized that the deployment itself becomes a bottleneck of being able to sell more and make more money, eventually being able to deploy successfully. And a lot of it is because the commissioning process ends up taking a long time, creating risks for the end customers. They're tedious and complex. They require skilled personnel. There's a lot of site shutdowns, adaptations, infrastructure, and compromises that people have to make with the current technologies. And what we set out to do, and eventually, I think what you can definitely sense as a hint, as kind of an underlying tone in the industry, that the end customers are cautious and resistant to autonomy, and much of it is because of deployment. And in other industries, in the consumer electronics, it's called the magic moment. But effectively, for those end customers, when they buy in, they decide to splurge on automation and autonomy, they want to feel it just works. And then seeing a solution that takes weeks to get set up, and then seeing how long it takes it to scale up from 10 to 100. I just had one customer today saying, yeah, we could deploy 3 to 5, but when we got to the 100, it became impossible. You realize that's where the bottleneck is, and that's very precisely put, right? And I think the end customers really reflect the feelings here, that this is not the way it needs to be, and not the way that to enable it to really work anywhere. And what we're doing at RGo to solve this is we're using a lot of perception and AI to simplify these processes. Analyzing these processes, and Jack is going to go through them in a moment, led us to believe, to understand that much of these, the tediousness and complexity in them, are a result of technology limitations and human involvement in the automation process. And I like to say that in many ways today, automation, or at least automation deployment, is very manual. And we want to automate automation. Okay? And with that, Jack, over to you.
Thanks, Asaf. Let's see. There we go. Okay. So before we get into what RGo is doing, let's talk about the problem statement, right? So for site commissioning, 2D systems have some critical limitations. Right? They require additional skill sets and time to stitch and edit facility scans before they're really a truly useful map. Then you have things like overhanging obstacles, partially empty racks, workstations such as desks and chairs, as well as guide rails that are all very common items in the field that do not provide enough data for a robot to safely plan an appropriate path in the real world. Conversely, there's also pallets and products staged on the floor and forklifts parked in the aisles that can temporarily be there while scanning and show up as spatial constraints, even though for typical operations, that isn't really the case. So what is RGo doing about it? What is our approach? So we've recently developed an intelligent map wizard that uses 3D data and semantic data to add valuable insights to the map immediately without the need of specific skill sets and long time frames to resolve. Right, what we were discussing previously with 2D systems requires a lot of rework and a lot of effort and activity, and usually long deployment times. Just recently, we had a customer go through a deployment at a site that had previously used LiDAR-based systems. Their engineering staff was very used to LiDAR-based systems. So they budgeted a week for deployment, budgeted a week for mapping specifically in the deployment. They planned for 3 days, and it actually took 2, right? So all of this effort is to get things from taking weeks and months to deploy, depending on your site's size and scalability, to get down to days to deploy, right? Take out the we'll say inherent knowns that a deployment engineer has to keep in their brain and identify while they're scanning the environment and make notes, tedious notes on what needs to be taken out and what needs to be added in and where, let alone, actually stitching LiDAR maps together, which for anyone that's actually done it, it's a pain. It's a truly pain in the ass. There's constant little minute tweaks that you need to make, right? And and if your stitching isn't just right, I know from a lot of my experience back in my auto guide days, if our stitching wasn't just right, then our virtual path would shift, would just step wherever that stitching is off, right? So we want to take all that out. We want to take that all out of the equation. For our system, there is no stitching. If you map an area of the facility today, and in 6 months or a year from now, the customer wants to add on a part of the facility, it just grows, right? All you do is you expand your drive space out into that area and just grow, right? But so enough about that. We'll get into the actual map wizard that we developed. I think it's pretty cool. So we'll go ahead and jump into a video and show you guys what we're up to. So right now we're just going through what would be a typical mapping process. So that was one customer robot. This is the real new customer robot, right? So mapping just involves manually driving the robot view, but through the house. And so from that mapping activity, we're able to create a three-dimensional reconstruction. We're able to then identify free space for the vehicle's travel. So you'll notice in the wizard here, it's a very sequential, step-by-step activity that leads the deployment engineer or leads the technician in a way that they're able to identify any of the potential objects or potential semantic data that's of particular importance, and either accept it or reject it, right? So the first step here is accepting the free space as it is. Right? And you just click next. And then the next step is to actually go through and review each of the objects that were identified. From the system itself, we're able to identify what we perceive as dynamic and moving objects. And you'll see here there's an image of demo robots that's hauled out in a particular space. So upping a robot should obviously be free space. There's a cart that stays at the end of an aisle that doesn't belong there, and that's free space. There's another cart over at the end of this aisle, free space. Hand dolly, that doesn't, that's free space. And here is what appears to be a movable cart, right? But operationally, this particular cart belongs there. Right? It might not spend 100% of its time there, but it might be 80 or 90%. Right? And so what's important is to maintain that is not free space. Robots should never drop into that area, whether or not it's usable. So that's where the user's able to blocked and then move on to the next stage. So once you've categorized your objects based off of how they impact your free space for path planning, now we move into more of the semantic data for understanding your actual environment. And so in this case, we're reading signage, right? So at the end of each of the aisles, there's an aisle name and number, right? A1, A2, A3. And there's also 3 additional signs in the back. And one for caution, one for danger, and for no forklifts. Right? So as you can see, the wizard just guides the user through to either approve or reject each of the semantic data that was captured, so that when your map is published, you're able to have what's useful and usable information to you and to your end customer. And so we'll go ahead and play this again. So when you click next, it locks it all in, and you go to publish. And once you publish the map, close it. And then you're able to align the map with the two-dimensional image, and have a clean representation of what is usable space and what is your actual environment. It might be a little hard to see in this image. So if you can see where the signs were in the wizard in the previous page, you can see that aisle 1 is labeled, aisle 2 is labeled, aisle 3 is labeled. We have the caution sign and the no forklift sign clearly labeled on the map. And again, going back to my AutoGuide days and my Mir days, I can't tell you how useful this would have been whenever I was evaluating my 1 million square foot warehouse facilities, right? And the customer is telling me that there's a robot is having an issue in aisle K, and I have no way of knowing which one is aisle K just from looking at the map. Yeah, you almost have to have your own key and then count the number of aisles over, starting from one end to the other. And no 2 facilities are the same. No 2 naming conventions are the same. However, one thing you can pretty much always guarantee, particularly in large facilities, is that there's going to be column numbers and or aisle signs, because that's how humans operate, and that's how humans navigate through an environment. So that level of semantic data
is almost always available, is almost always readily available and easy to process. So that's why it's such a big part of improving not only the initial deployment, but also the maintaining of the deployment down the road and for operations. So we're very big believers on, this is where Asaf was talking about the different levels of AI and semantic understanding of our environment. These are some of the key points that we believe really unlocks the next level of efficiency in operations. So enough about that. I'll show so you can see that the robot is able to drive along the map, and then after it's all been categorized, classified, and the semantic data has been locked in, and the image has been aligned to that, and then it's just a matter of start up your own system and let your robot move.
All right. So again, that wizard, the mapping wizard that we were just launching, we believe is a big part of short and simple commissioning, right? We believe it's going to really help our partners to have more efficient deployments, shorter deployments, less skilled personnel doing deployments, right? And who knows, maybe eventually it actually gets to the point where end customers are able to do deployments, and your actual deployment projects aren't even required, right? It all depends on how customers and the OEMs choose to handle that business. All right. So the next area that we'll discuss is time to market, right? So getting into the time to market, I think one of the biggest things, the first thing to really address is that our perception engine is a fully developed, ready to deploy product, and it's already deployed and it's already scaling, right? So it's not a kit, it's not a framework. It's not something that you use as a base and then have a team of your own engineers build on top of. Right? It's a product. Right? And as a product, we support 4 main client types from an API perspective: ROS1, ROS2, UDP, and C++. The ROS and UDP APIs are typically used for evaluation purposes. So those are great protocols for specifically standing up a new robot, a new system immediately, and then getting it set up and using our user interface so that a customer can go about doing an evaluation of our system immediately, right? And so what we mean by immediately, typically it's a 1 to 2 day integration, but we usually schedule a week of integration support. That's to get the robot stood up with our system, and then provide some training on the UI and how to do repeatability testing. And so by the end of the week, we want to arm up our prospective clients or prospective partners with enough information on how to address and evaluate the system for themselves. So at that point, they typically have a month to evaluate the system, and then they're able to really make a true decision on whether or not it's the best fit for their use case. All right. So this slide here shows some of the key features that are available in the full C++ API. Right. I think the most important takeaway here, this looks complex, but it's really just a large number of features and some initial configuration that's done on day one and never touched again. But the biggest takeaway is that our only requirement, if you're using our monocular system, is that you're providing us wheel encoder data, and then we're providing you 6 degree of freedom pose estimation. So it's really as simple as that. In ROS, it's a couple of topics that are monitored. But ultimately, there's not a whole lot involved in standing up an evaluation of the system, and there's not a whole lot involved in setting up a production-ready system. All right. So again, just kind of really hitting the point on easy to integrate. We already touched on that there's a number of APIs that we support. Our communications are through Ethernet, and we can do CAN bus, but pretty much everything is piped through an Ethernet cable. Again, we really just need your wheel encoder data for odometry. If you want additional sensor fusion, like for example, if you want to leverage our obstacle detection or obstacle avoidance libraries, then that's something that we can also incorporate into our sensor fusion. I'll be honest, most of our customers are purely focused on the localization because that's the pain point, right? They all have some flavor of obstacle detection already developed, but localization and reliable localization is what's really hindering people today. So another important element that I'll touch on here is that our software can either be run on a shared compute or its own compute, standalone. So from an evaluation kit perspective, we'll provide our own compute in the form of an evaluation kit. So the camera, the sensors, and the compute are all in a box. You mechanically fasten that box to your robot. There's set up a short config file for where that camera is in relation to a reference point. A few other details here and there to set up your calibration, and then you're off and running. What a lot of our customers prefer is to actually use our reference hardware design. So we tell you what computes to use that can be used, what cameras to buy with the integrated sensors, and then you're able to manage your own BOM costs and integrate the system into your own robot rather than bolting on a box. But we honestly have customers that do it either way, so it doesn't matter to us. Next slide. So now I'll just kind of walk through the typical partner's journey, and this is all again coming back to the time to market, right? So for our system, the way it generally works is we have an introduction call. It's usually 1 or 2 calls where we hammer out some of the details of, how are you going to mount the mechanical, it's going to be the mechanical fastening of the box, where's it going to be placed, what are the electrical requirements, just some of the immediate details for attaching any sensor to any sort of robot and expecting something valuable from it. So of course, over those 1 or 2 calls, we then get into scheduling an evaluation. So we schedule that 1 week for the first integration, where we help to integrate our system to your robot, and then we also teach to our documentation and our user interface and how to do the specific evaluation testing. Then we give you 4 weeks on your own to do whatever you want from an evaluation perspective. Check repeatability, check different environments, check dynamic changes to your environment, see how everything performs, check kidnapping, check lifting the robot, all sorts of different activities that are usually addressed. And there's usually an evaluation report, and that generally rolls into a commercial agreement. And then from the commercial agreement, then it's really a matter of planning out how you're going to integrate the robot, our system into your robot's environment, right? Are you going to buy a bolt-on box? Do you want the reference hardware design? How are you going to design it into the mechanics of your robot? already? What's your next generation look like? Those are the kind of design questions and we'll say hurdles that we overcome over that 4 to 6 week period. And then it generally comes to a hardware integration. Most customers do, 1 or 2 robots, full hardware integration first, and start to do a little bit of testing with that. And the full API integration is also tied in. So that's usually a 1 to 2 week activity, but it doesn't require the hardware to be there. It's all just about setting up the image ahead of time, and then after full integration happens, then there's usually some level of validation testing before you're really offering it to the market. But ultimately, what we're seeing on average is between 3 to 5 months from starting with an existing robot, no localization solution, or you're replacing an existing solution, to having an actual deployable robot that's available for the market with our solution involved. So from a total cost of ownership perspective, talking about 3 to 5 months of just integration timeline to have a proven product integrated right into your robot, versus if you decide to build it internally, which a lot of people do, a lot of people try. But what they quickly find is that they invest years of development time and millions of dollars developing a SLAM solution that still is years behind what's already been developed. So that's our spiel on time to market. So coming back around to what are the 4 major things that are the difference maker between Autonomy 2.0 and Autonomy 1.0, is that everywhere, always, adaptable, short and simple commissioning, and fast time to market, right? So these are the challenges that we seek to overcome for our partners. And so with that, I would like to say, recognize some of our hardware and software partnerships. There's a lot of great people that work with us, and we really highly value them. Cherry does some really great work for us. We use their boards for a lot of our products in the field, as well as NVIDIA. They're also heavily used in the field. So really appreciate our partnerships from a platform perspective. We're also integrated with InOrbit, Miley, and Navitec Systems. So really appreciate those partnerships as well. They bring a certain level of fleet management to our operation. So that's one of the great things about that, is really for our secondary market, which is manual forklift tracking. We're able to incorporate live positional data for forklifts in a facility, feed that to a fleet manager, so that robotics vendors such as yourselves are able to understand where forklifts are at and make more intelligent decisions from a traffic planning and path planning perspective. So we really highly value those relationships as well. Especially they strive to achieve the VDA 50/50 guidelines, which just makes talking to and working with everyone a lot easier. Yep. I'll pass it back off to Asaf.
Yeah, thank you for that. So as we saw, right, what we focused on is enabling robots to operate seamlessly, enabling robot manufacturers to just have operational systems anywhere, anytime. As the systems evolve, what we're spending more and more time and more focus on is enabling more semantics and more information of the environment. And we believe this information is the key, and it's going to drive the next generation of products. And that's not coincidental. That really aligns with what AI is doing and how AI operates. So AI requires information. And what we're driving to is to increase the level of information to enable more and more complex and intelligent use cases. And that level of information is what's enabled the frictionless commissioning with the wizard that Jack has demonstrated, or now that we have finally automated much of the required information for commissioning. And we will also add more and more layers of information over time to that wizard. We're also using the same information to also synergize with a digital twin, with AI agents, with AI insights, with chatbots, and basically bridging the gap between real to sim and sim to real. So this information platform that we're building that is heavily collaborated with NVIDIA and their offerings is focused around bringing more and more value and understanding by the way of semantics and geometry into the world of robotics, and synergizing this with all the AI offerings there that are available today in the market. So you could have a full digital twin representation automatically, and you wouldn't have to worry about how you do that. You would be able to use a digital twin in between, back and forth from real to sim and sim to real seamlessly. Okay, and that revolution is going to be driven by information. I know the robotics industry is a very skeptical one. I've been around in this industry for, I would say, more than 10 years, if not 15. But looking at the world the last year, if not 3 years, this revolution is coming. And this is how robotics would need to work with this revolution to really extract value. We cannot just focus on predefined coding. We need to make sure that we enable this to be more scalable and more interface with AI. And for that, we are building the information platform going forward. So this is where we're going to drive frictionless commissioning, and the commissioning wizard is the first step, but we're definitely not stopping there. So just in time, I want to thank you all. And I think now is a good time for questions.
Okay. Asaf, Jack, thank you very much. Very interesting. I noted here some questions from the people. One thing, I have a question because I saw there were some questions about that. Today is very, it's trendy. We have more and more applications outdoors. And there was some questions asking what are the limitations in terms of fog, rain, snow, if there are any limitations, because we know from the typical, let's say, 2D laser scanners that in fact they suffer sometimes some limitations in terms of millimeters per hour or all these things. What about your system?
Sure. So I'll take the first stab at it, Asaf, and you can add on if you'd like. But it's a great question. So obviously, environmental impacts that would hinder visibility are challenging to deal with, right? So what we choose to leverage and what we believe is a very good approach is to use our sensor fusion. And specifically for outdoor environments, we're able to, additionally add in the RTK information as well to get that extra modality of positioning data, right, in order to maintain a high level of robustness, right? But just even without the RTK data, we have the IMU and encoder-based data that is good for a small distance if you're completely blind, but ultimately the more modalities that you introduce, the better you're able to actually overcome some of those challenges.
Okay, and there was some other questions because we are talking about correct me if I'm wrong, substituting somehow the typical 2D LiDAR navigation or localization, okay, with a vision which requires some kind of hardware. Is there some kind of hardware requirement from your system, or let's say I would say agnostic from the hardware point of view? What do you need in terms of hardware? Let's put it this way.
Sure. So we have some reference hardware that we are already integrated to, right, and that we know performs rather well. And there are various tiers, right? There's premium, standard, and we'll say more budget-friendly cases of hardware. I would say that the drawbacks for the different tiers are that you end up with a higher level or lower level of features that are available. So not all features that are available on a premium tier will necessarily be available on a more budget-friendly one. Just to name a few, so Cherry's Jaguar board is a big one for us that we use a lot. We integrate with some NVIDIA GPUs. Asaf, correct me if I'm wrong. I want to say it's the AGX.
No. So yeah, it's fine. So I think on the hardware platform side, we're operating on many compute systems. We're operational on a ROC chip by a Cherry Jaguar system. We're operational on NVIDIA Orin across the family, all the way from Nano, NX, NX16. Obviously, also on the AGX if you splurge the bucks. We're also operational on a Qualcomm platform on their RB offerings, and we're now getting a ramped up also on the Raspberry Pi. So the general answer is that compute systems are not the issue. They're very easy to port to. We can run native, but we also support a Docker and deployment that makes it simple. The secret sauce is more about the reference that we provide for the sensory suite, and that's the crucial part. And we've spent some significant time optimizing that. So the reference design is not only guaranteeing high performance, but it's also very affordable and easy for high volume manufacturing, which is crucial for scaling. If we could have selected very expensive sensors that are hard to integrate or very hard to source or exotic, that would be challenging. But we provide open references that you can use and you can take to your own production team, and they can integrate them, and you can get a very low cost of sensory suite. It can be as low as $10 or $20, depends on your use cases and your sourcing team and quantities. So in that regard, you can integrate this into any robot. We provide open reference hardware design, whereas we effectively provide the software solution.
Okay, and always talking about requirements. Okay, what is the computing requirement that you need, or compute hardware that you need?
That also very much depends on the performance and the feature set that you're looking for. But generally speaking, we can run on almost any system that has a quad-core ARM CPU in it, even a Raspberry Pi.
Even in Raspberry. Okay. Then I want to show you a couple of specific questions. Okay. Let me check. You can see it. Okay. So Danjam is asking a couple of questions about calibration. The first one is about calibration. So how does calibration work? So it's a camera pose or versus a reference point on the vehicle. It's manual, automated, semi-automated. How it works, their calibration?
Yeah, I can take this one as well. So I think calibration is a very interesting and very important topic. And we're building basically, if we dive to the details, this is an estimation system for localization. And any estimation system is limited by the accuracy of its measurement, which is limited by the accuracy of your calibration. So calibration is a crucial part of estimation and thus accuracy. And we've actually spent a lot of time creating a specialized calibration pipeline that starts all the way from the production phase and all the way down to the online device. And we try to do much of the calibration automated as much as possible and not to fuss the robot manufacturer or the end user about it, especially not the end user. So in that regard, the only calibration you need to do is to calibrate the robot once by turning it in place when you take it out of the box. That is automatically stored on the device. That's part of the commissioning. It takes maybe a minute if I'm exaggerating. It's also mitigated either by the UI or by the APIs. You can do it either way. And that means that the robot is now calibrated and ready to deploy. From there on, we also make more effort to constantly and continuously calibrate and recalibrate the sensors, not just camera to body, but also internally sensor to sensor, to make sure that we get the most optimal performance. And we spend a lot of efforts on that. So that's a very good question. I like it.
Okay. Always Danjam asked, it's different now, but is it possible to semantically detect pallet location during mapping process?
So mapping process means that you're focused on dynamic or static obstacles. And yes, we could detect pallets during the mapping process, but this is, I just want to clarify because pallets have also a very common use case about pallet engagement, which is a different use case. So for mapping, yes, we could detect pallets that say are placed on the floor and mark them up as movable obstacles that should not be there, right? So you can clear up your free space and say, yes, I want this to be free space, which is a different feature completely from pallet engagement.
Okay. Then another topic. Okay. Of course, your system is sees the environment, recognize and make the robot work in a given way depending on what is seen. Okay. How does it work? I mean, or have you worked with your customers in terms of safety? Okay. Is there some kind of how do you work? I mean, let's put this in a more broad point of view. Is your system somehow safety certified, or what are doing your customers in terms of safety? Because you are also avoiding or let's say of collision avoidance, the infrastructure, the people. How does it work?
So safety is a very tricky topic, right? Because safety first and foremost is only approved at the system level. So even if we had a safety certified system, which we do not, you will still have to reapprove it at the full system level. And this is also very dependent on your industry, your application, your geography, and your end customer requirements. So this is a very complicated question. What we do provide is we know what are the data that is required by our customers to safety certify their system. It is crucial to know that our systems and the perception that we provide is not targeted for safety applications. So we do not detect obstacles just say like a LiDAR scanner might, as far as being safety certified and shut down the engine. But we do provide data for applications that have mixed operations with less critical impact scope, that they can work on data-wise to get their certification for the safety side, right? So,
well, it's a question of risk assessment at the end of the day, no? Asaf?
Exactly, yeah. We know what the data is, and we know how to provide it for risk assessments, for safety, for systems that do not require a physical safety sensor. Okay.
Okay, and then I would say that well, this let me know if you can answer to this, because it's specific. If there's an angle of perception for azimuth or for the elevation.
I'm not sure I understood the question.
I'll
try to answer it the best I could. Is basically,
but I think it depends more on the camera, no? Or...
So the camera can be placed anywhere as long as there is sufficient field of view that is open, and the system provides full 6 degrees of freedom, so including X, Y, Z, the OP troll, or as a quaternion, which is obviously our always preferred. And the system operates in any elevation, so we can't support a drone application, but we do support ramps and slopes. You've seen one in the demo that Jack showed about a car going down into a parking lot, and they actually went down 2 floors there. So that's not a problem. We can walk outdoor in very slopey and very high degree of terrain elevation.
Okay, well, I mean, there are a few other questions, but we are running out of time now, and I think that we can leave here. Let's put the AV so we can see you. Okay, I think that we can stop here the presentation. Thank you very much, Asaf, Jack. I will share the presentation with all the people here today. Also your contact details, so in case they have some more specific questions, they can contact you, okay? Just one reminder, because you will be at the Logimat, if I'm not wrong. Will you also be at the ProMat?
Yes. Yeah.
Okay, so you will be the next week and in the Logimat, and the week after at the ProMat. So there's a great opportunity also to meet you in person, you or your team, okay? And to have a better understanding of how can you integrate your perception system into the mobile robotics. So if everything is fine, I mean, you have something else to add, Asaf, Jack, otherwise, let's say it's finished.
No. Feel free to reach out to us if you have any questions. I know there's a list of questions, so try to follow up on some of them.
Thank you. Thank you, guys.
Thank you as well.
Ciao,
Bye-bye,
Sat. Thank
everybody.
you very much.
Bye-bye.
Thank you,
Ciao.
Jack.
Thanks, guys.